Electronic Devices, Junction Diodes, fourth part, series on Semiconductor Devices and Circuits, lecture number 2.14. The term diode, it has been formed out of two words. One is die, another is electrodes. Die means two. Electrodes refer to charged metal rods. In diode, there exists two terminals. It is formed out of two differently charged rods, metallic rods. That is why it is called diode. Diodes can be made with vacuum tube technology, or they can be made with semiconductor technology. Here we are concerned with diodes made with semiconductors, or diodes which are called PN junction diodes, or simply junction diodes. Basically, diodes, including semiconductor or junction diodes, are nonlinear, unilateral, passive devices. They exhibit rectifying properties. They have plenty of applications in the design of electronic circuits. In the present session, which is fourth one on junction diodes, the focus is on internal currents, that is, currents inside the diode, energy band diagrams of the diodes, and also on behavior of the diode under biased condition. All these aspects, we not only touch them, but also we try to go a little bit deep so that our understanding is maximum possible. With this few words of introduction, now let us move to start the session. We begin the session with a few remarks regarding internal currents. What are internal currents? Consider a diode. P region on one side, N region on the other side. If it is forward biased, current enters into the diode from P region side. Let us say this current is I. The current that is entering into the diode, this current is called terminal current. After entering into P region, this current can be considered to be split into two parts. One part due to movement of holes, another part due to movement of electrons. Similarly, the current that has passed through P region enters into N region. In N region also, the current can be considered as consisting of two parts. One part due to flow of electrons, another part due to flow of holes. After passing through N region, again the current comes out of N region into cathode terminal. Then it again, of course, it is equal to I according to Kirchhoff's current law. Now I, left side, I, right side, these are called terminal currents. The current due to holes in P region, this current is called majority carrier current in P region. The current due to flow of electrons in P region, this is called minority carrier current in P region. Similarly, when we come to N region, the current component that exists due to flow of electrons, it is called majority carrier current. Current due to holes is called minority carrier current. Terminal current is always, notice, it is equal to majority carrier current plus minority carrier current, either in P region or in N region. One more point also required to be told. Both in majority carrier current and minority carrier current components, in each one again there exists two parts. One part due to drift, another part due to diffusion. So in total, if we consider in P region that exists 4 parts, in N region also that exists 4 parts. These 4 parts, they are called internal currents. Sum of internal currents is always, as already mentioned, equal to terminal current. All the time, majority carrier current plus minority carrier current is equal to terminal current. Minority carrier drift current is negligible. Why it is negligible? Drift current is proportional to carrier concentration. It is also proportional to potential gradient. In P region or in N region, minority carrier concentration is low, negligibly small, because they are minority carriers. This is one aspect. Second aspect is P region and N region. Their conductivities are very high. Therefore, potential gradient is very, very small in both these regions. As minority carrier current is proportional to carrier concentration, it becomes low. As it is proportional to potential gradient, it becomes further low. It becomes so low that one can neglect it. For this reason, minority carrier current is nearly equal to its diffusion component. Minority carrier current is sum of drift component plus diffusion component. When drift component becomes 0, the total current then becomes diffusion component. Of course, it can be shown this diffusion component falls exponentially with the distance from the transition region. This can be found with rigorous mathematical analysis. This is an important point. Diffusion current falling exponentially with the distance from the transition region. Therefore, minority carrier current falls exponentially with the distance from the transition region. Majority carrier current is difference between terminal current and minority carrier current, and hence it rises exponentially with the distance from the transition region. Total current is minority carrier current plus majority carrier current. Here minority carrier current is falling exponentially with the distance. So naturally majority carrier current rises exponentially with the distance from the transition region. At the transition region, majority carrier current on one side becomes equal to minority carrier current on the other side. Why? Reason is, notice, P side whole current is majority carrier current. This current then, when it enters into N region, it becomes minority carrier current. During the travel through transition region, no recombination happens, or recombination that happens is negligibly small. So naturally, current on P side is equal to current on N side. On P side, it is majority carrier current. On N side, it is minority carrier current. Therefore, At the transition region, majority carrier current on one side becomes equal to minority carrier current. These two transition points are determined by relative concentrations. In this slide is shown various points which we discussed in the previous slide. Here they are shown in the form of a picture. Two situations are considered. In situation A, in diagram A, donor impurity concentration is very, very large when compared to acceptor impurity concentration. In B, acceptor impurity concentration is very, very large when compared to donor impurity concentration. So two components are shown on both sides. IPN stands for current due to holes on N side. This current component has two parts. One part is due to drift, another part is due to diffusion. We have already understood that drift part is negligible. Therefore, the current, minority carrier current, whole current on N side is entirely due to diffusion. And the diffusion current falls exponentially. This is exponential fall. Total current, electron current plus whole current is equal to terminal current. When whole current falls exponentially, it is falling exponentially. Electron current naturally rises in an exponential manner. So that total current becomes equal to the terminal current. Similarly, when we come to P side, INP is minority carrier current. It is current due to electrons on P side. The symbol has a meaning, and it is told that minority carrier current is due to diffusion, as drift current is negligible, and diffusion current falls exponentially from transition region. This is exponential fall. As majority carrier current plus minority carrier current has to be equal, as minority carrier current is falling exponentially, majority carrier current has to rise in the same manner, exponential manner. And this is the situation when ND is very, very large when compared to NA. When NA is large compared to ND, the situation is depicted here. On N side, notice the whole current is falling exponentially. Electron current is rising exponentially. On P side, whole current is rising exponentially. It is majority carrier current. Electron current is falling exponentially. Now we consider energy band diagram of a diode. P region left side, N region right side, in between junction region. EG stands for band gap energy, forbidden band gap energy. EGP is there. Sorry, it is ECP, not EGP. ECP. E stands for energy, C stands for conduction band, P stands for P side. Similarly, you can see EVP, energy, valency band, P side. Similarly, here EVN, energy, level of valency band on N side. Similarly, this level, energy level, can be designated as ECN, energy level on N side of conduction band. At the bottom is valency band on both the sides of the diode. At the top is conduction bands. In the band gap, there is one energy level indicated by EF. EF stands for Fermi energy level. Fermi energy level indicates average energy of the electrons. Notice this level is constant. It is same both in P side as well as N side. Another energy level is indicated in this diagram, E naught. What is E naught? E naught is equal to E. E means charge on the electron multiplied by barrier potential V naught. EV naught. EV naught equal to E naught. Barrier energy, that is E naught. Notice in the diagram, the band gap is at a higher level when compared to band gap on N side, or on N side, band gap is at a lower level when compared to band gap on P side. EF is near to EVP on P side, and it is near to ECN on N side. The band gap takes transition from P region to N region, from high to low during space charge region. So these are some of the points one has to keep in mind. Some more points we'll discuss further in this session in the next slides regarding energy band diagrams. In ordinary rectifier diodes, the contact difference potential energy, that is E naught, it is always less than the band gap energy, Eg. That is, E naught is always less than Eg. In the diodes, the conduction band and valency band energies are related through ECP minus ECN is equal to EVP minus EVN. It is equal to E naught. ECP minus EVP is equal to ECN minus EVN equal to EG. These energy levels, they are already identified in the diagram in the previous slide, so they don't require further explanation. ECP, it is conduction band energy level on P side. Second one is energy level of conduction band on N side. The difference is equal to E naught. Same or similar is the case with the difference between EVP and EVN. Similarly, ECP means energy of conduction band on P side. EVP means energy of valency band on P side. The difference is equal to Eg, band gap energy. In equilibrium, under no bias conditions, the Fermi energy level remains at the same position on both sides of the diode. Whereas under bias, the Fermi level of two regions get separated by an amount equal to the product of E, that is charge of the electron, and the applied voltage. The diagram that has been shown as energy band diagram of diode, it is valid when the diode is under no bias. Charge balance equation. This equation is quite useful in understanding the properties, the behavior of transition region. The penetration depth of the depletion region within a particular side of the junction, it is inversely proportional to the doping concentration on that side. Mathematically, it can be stated as WP naught NA product is equal to WN naught ND product. So what he is telling is this. This is diode, P region, N region. Here transition region exists surrounding the interface. The transition region or junction region, usually it is not of same spread in both the regions. In one region it is more, in one region it is less. So in P region, let us suppose width is WPO or P naught. N region, it may be WN naught. NA is, of course, impurity concentration on P side, Nd is impurity concentration on N side. These widths of the junction region on P region side, N region side, they are dependent upon the impurity concentration. They can be related. That relation is charge balance equation. Wp naught Na is equal to Wn naught Nd. Another law we consider, law of junction. It gives the free electron hole concentration at the edge of the region, at just outside the transition region, in terms of thermal equilibrium minority carrier concentration far away from the junction and the applied potential. What this law says is, this law gives free electron concentration or hole concentration. For example, this is P region, this is N region. Electron concentration on P region, where just at the edge of the transition region here. Electron concentration here, N, P, or hole concentration on N side here, minority carrier concentration, Pn, just at the edge, means 0, 0. This law gives these concentrations in terms of minority carrier concentration at thermal equilibrium and the applied potential. This law is quite useful in deriving the diode equation. Let us see what this law actually says. Np of 0, 0 means at the junction. Np stands for free electron concentration on P side at the junction is equal to Np naught. Np naught means electron concentration on P side under equilibrium condition, multiplied by e power V by Vt. P applied voltage, T means it is a constant volt equivalent of temperature. It is 26 millivolts at room temperature. Similarly, Pn of 0 is equal to Pn naught e power V by Vt. Now a few points regarding diode models. Vi characteristic of the diode, we know under forward biased condition it is exponential rise like this. Under reverse biased condition it is constant current up to certain voltage. After breakdown there is a sudden rise in current or fall in the characteristic like this. So this is actual characteristic. This has been derived from the equation, diode equation partly, and remaining is from reality. This fall we can see, this fall we can know from experimentation. This total characteristic, this has been, for the sake of modeling, it has been divided into 4 parts: forward conduction, forward blocking, reverse blocking, reverse breakdown. Here the slope is, inverse slope is RF. Here nothing, no slope, it is flat. In third part, inverse slope is RR. In fourth it is RZ. So dividing the characteristic or replacing the characteristic with the straight lines, it is called piecewise linear modeling of the diode. Certain diode models are shown here. In A, 3 models are there. First one is called 0th order model. Second one is called first order model. First order model. Third one is second order model. These 3 are for forward bias diode. Depending upon the exactness you require, you can go for either 1 or 2 or 3. Out of these 3, third one is more exact than the remaining 2. Models that are suitable for reverse bias diode are given in B. 1, 2, 3. Out of the three, of course, third one is more exact when compared to the remaining two. Here we have used certain sources V gamma and Vz. V gamma stands for cut-in voltage, Vz stands for Zener voltage. Right side we have shown small signal equivalent circuit of PN junction diodes. In A, certain resistance RF, Rn, these two resistances pertain to the resistance of P region and N region. CD stands for diffusion capacitance, RF stands for forward resistance of the diode. CT stands for, in B, transition capacitance, RR stands for reverse biased resistance of the diode. Under forward bias, under reverse bias. A, forward bias, B, under reverse bias. Diode breakdown. In diodes, breakdown can take place under both types of biased condition. Under forward biased condition, when the voltage approaches built-in potential, the diode starts conducting large current due to disappearance of barrier potential. It results in heat generation and subsequent rise in temperature of the diode. If the diode is not designed to handle the heat dissipation and consequent rise in temperature, even burnout may take place, or the diode ceases to exhibit rectifier properties permanently. Before going further, let us ponder over the meaning of breakdown. What is a breakdown? If the behavior of a device deviates abnormally from its expected behavior, then we say that device is under breakdown. Diode is supposed to behave in a particular manner, in a certain manner, governed by diode equation. If it departs heavily from the diode equation in its behavior, then we say diode breakdown has happened. Two types of breakdowns are there: forward breakdown, reverse breakdown. A few points are considered regarding forward breakdown. Now it is about reverse breakdown. Under reverse biased condition, diode equation predicts flow of small amount of current, reverse saturation current, through the diode, irrespective of magnitude of the applied voltage. However, in practical diodes, if the biasing voltage is equal to certain value called Zener voltage Vz or breakdown voltage VBR, a substantial amount of current flows through the diode, and in this region, a very small increase in reverse bias voltage results in a very large increase in diode current. So deviation is there. Deviation is not normal, it is abnormal. So we say breakdown has taken place. The magnitude of the current that flows when V approaches VBR can be predicted from the following experimentally determined relation: I equal to I naught by 1 minus V by VBR power n. N is a constant. Its value is between 2 and 6. Large currents generate heat and consequently temperature rises. If it is ordinary diode without any precautionary measures to handle such high temperatures, permanent damage can happen. This is all about reverse breakdown. So important aspects to be kept in mind right now here is: 1. Forward breakdown happens when applied voltage approaches built-in potential. Reverse breakdown happens when applied voltage approaches Zener voltage or breakdown voltage. Now we consider a few points regarding diode under bias. We consider both biases side by side so that a comparison is made possible. First forward bias, then reverse bias. The P side is at a higher potential when compared to N side in case of forward bias. N side is at a higher potential when compared to P side in case of reverse bias. Of course, this is the definition of forward bias and reverse bias. The diode offers low resistance under forward bias, whereas the diode resistance is very high under reverse bias. The diode resistance is inversely proportional to diode current under forward bias. The diode resistance is almost fixed independent of diode current in case of reverse bias. It is large valued diffusion capacitance that dominates junction capacitance under forward bias. It is a small valued transition capacitance that dominates the junction capacitance under reverse bias. The junction barrier height gets reduced from EV0 at equilibrium to EV0 minus V. This is under forward bias. So barrier height decrease takes place under forward bias. Barrier height increment takes place under reverse bias. Reverse bias increases the barrier height from equilibrium value of EV0 to EV0 plus V under reverse bias. Some more points. The electric field intensity across the junction decreases in magnitude. This is under forward bias. Under reverse bias, the field strength across the junction increases. Under forward bias, shrinking of depletion region takes place, whereas under reverse bias, width of space charge region increases. Under forward bias, there exists decrease of charge in the depletion region, whereas reverse is the case in case of reverse bias. Under forward bias, a substantial increase in diffusion current takes place due to reduction in barrier height. Thus, more electron diffusion from N to P side and more hole diffusion from P to N side takes place. Diffusion component of current decreases appreciably as compared to its equilibrium value. The total current of the diode is contributed almost by diffusion under forward bias. That's why forward current is also called diffusion current. The drift current dominates under reverse bias. This drift current is from N to P side. This current is called a drift current or reverse saturation current of the diode. Some important relations pertaining to diodes are given here. Let us go through them. Charge balance equation. The product WPNA is equal to WNND. Junction width dependence on doping level. W is inversely proportional to square root of ND. Junction width dependence on bias voltage. W is proportional to Vj, junction voltage. Law of junction is Np of 0 is Np0 e power V by Vt. Similar is the case with hole concentration. Contact difference of potential V0 is equal to Vt multiplied by natural logarithm Na Nd by Ni square. This can be put in terms of electron concentration or hole concentration in equilibrium. Shockley diode equation is there. It is I equal to I0 e power V by eta Vt minus 1. Reverse saturation current depends upon diffusion length, diffusion constants, and also concentrations of electrons and holes. It is given by AE. A stands for area. E stands for charge on electron. It is equal to dP Pn0 by Lp plus Dn Np0 by Ln. This can be converted into another form where there is intrinsic concentration. Temperature dependence of diode current is given by one equation. I0 of T is equal to I01 into 2 power T minus T1 by 10. Temperature dependence of voltage is given by dV by dt equal to minus 2.5 millivolts per degree centigrade. Transition capacitance Ct is dq by dV mod. It is epsilon A by W when the diode is heavily biased on one side. For the same case, diffusion capacitance is tau G equal to tau I by eta Vt. By definition, of course, it is CD is equal to dq by dV. With this, we come to the end of the session. Before closing down, let us recollect important points that are discussed in the session. Internal currents of the diode, they are considered, and then energy band diagrams of diodes. After that, diode models and diode under biased conditions, and at the end we considered important relations pertaining to diodes. Hope this session is useful to you. We meet again with a new topic in another session.